Hey everyone, welcome back. In the last of these little videos we talked about this new prescription drug model where we derived the model, and I've got the picture here to kind of summarize it. We looked at this bouncing behavior between, we took the drug and then it decays away and then we take another dose and then it decays away and then we take another dose and it decays away and then we take another, you get the idea. And we kind of saw this idea that as you take the drug for a long time, we were wondering what happens. At the beginning, the amount of drug in your body is going to ramp up over time because each time you take the dose, the concentration goes up, but then it doesn't decay all the way to zero. And then you take another dose, so it goes up the same amount as it did the first time, but it wasn't zero this time, so it's gone a bit higher on the graph. And so you'd expect that these maximums here, the value here, the value here, they're slowly getting bigger, right? Because each one's bigger than the one that came before it because it didn't all decay away last time. And so that kind of makes intuitive sense. And we came up with this sort of picture. We took a limit as the number of doses goes to infinity, and we found this finite number, right? So in other words, the residual left in the body after the nth dose decays away and we're about to take the next dose, because remember the gap between every one of these doses was always the same. We waited a time capital T between doses. The residual of that isn't zero. This R thing is not zero. So over time, you expect the residuals to kind of approach this finite number. And I kind of drew it like this, approaching from below, as in the residuals slowly build up over time, which I hope makes intuitive sense, because each time we go to our higher concentration than we had before and then decay down, and we don't quite make it down as far as we did before, and then we go back up here. I want to talk about that a bit more, and then we'll talk about this long-term behavior a bit more in detail. And our goal today is really to think about dose scheduling. Because remember last time I said at the beginning there's some kind of transient behavior. It happens for small numbers of doses, but in the long run we care about what happens after we've taken lots of doses. So that's kind of the long-term behavior up here. So let's kind of summarize some of the mathematics we had here. This is the limit we took, but as we were doing this calculation, we calculated the residual after n doses. And remember, we have a picture that looks something like this. So we've got the residual and the concentration after the nth dose has decayed, in fact. So the idea is the nth dose has decayed away, and we're left with this number R sub n, and then we take the n plus 1th dose, and we end up with this concentration C sub n, and then that n plus 1th dose then decays away to this value. And then we take the next dose, and we get this bounce. And so we worked out an expression for R sub n, and we wrote it, in fact, as a series. And then we took the limit, and you see that on the previous page, I actually had the limiting form written down. It was C naught divided by e to the kt minus 1. And all I'm doing is dividing by that C naught. So I've rewritten it here with the C naught divided over to the right, over to the left. But it's the same idea. Or without taking the limit, we've got that. And now I'm arguing that there's some kind of residual limit R that these values are getting closer and closer to. So as I look at the residual here, and the residual here, and the residual here, they're getting bigger and bigger, but they're going to approach, if I kept drawing them, they're going to approach that purple line, and they're not going to cross that purple line. That's kind of the argument I'm making. The limiting residual, which is this quantity, actually we approach from below. How can you see that? Well, here's the nth dose. Imagine what the n plus 1th dose looks like. The n plus 1th dose looks like the nth dose with one more term, because I've got an n plus 1 kt there. And that number that I just added on to get the n plus 1 dose, it's positive and it's not zero. So it's greater than zero. And so, just looking at that, you can see that the n plus 1th dose must be bigger than the nth dose, because I've literally added something on. This number out the front's positive, I've added something on in the bracket here, and so this value is bigger than this, because all I did was add another term on there. So each residual is bigger than the one that came before, right? R sub n plus 2, by the same argument, has to be bigger than R sub n plus 1. And if you think about the residual dose, the final limiting residual dose, in other words, I think about this in the limit as n goes to infinity, then I never stop writing down those extra terms. There's an infinite number of terms being added on here. This is an infinite series. So I just keep adding numbers there. So it's got to be bigger than any of the ones that I've talked about. In other words, it's bigger than Rn, it's bigger than Rn plus 1, it's bigger than Rn plus 2, because I'm just keep adding. So that thing, that limiting dose, is bigger than R sub n for all n. And so we're approaching this limiting dose, but we're approaching it from below. So mathematically what I'm saying is that R is bigger than R sub n for all of our n values. And they're all bigger than 0, that's kind of obvious. But all I'm saying there is that this is just an increasing list of numbers, sequence of numbers, and that sequence of numbers approaches R in the limit. So that gives us an idea of what happens in the long term. So let's look at a couple of special cases. To begin with, suppose this quantity Kt is much bigger than 1. And remember, K is the decay rate. So a large decay rate means that your body clears the drug out really quickly. And T is the amount of time between doses, which means you're not putting a lot of the drug into your body. So you're both not putting a lot of the drug into your body and it's being cleaned out really quickly. If that product is much bigger than 1, then e to the Kt is really big. All right? E to the Kt, this is an exponential. Kt is much bigger than 1. If Kt is bigger than 1, if you imagine what the exponential looks like, there's the Kt axis. If Kt was 0, that exponential would be 1. If Kt was 1, this would be e to the 1. That would be the value here. And then I'd be subtracting 1, so this would be some value. But if Kt is really, really big, then e to the Kt is really, really big, and this whole quantity is going to be really, really small, right? Because e to the Kt is really big, and that means 1 over it is going to be really, really small. And so in this case, the residual is close to 0. What does that mean? If you go back to thinking about the graph, then the residual after each clearing period is close to 0. You know, there's 1 period, and there's 2 periods, and there's 3 periods. The long-term residual is what I'm interested in. It's really close to 0. So there's the long-term residual. It's really close to 0. In other words, each time you take the drug, it's effectively cleared out of your system by the time you take the next dose. And so the long-term behavior is going to look a lot like this, and the concentration is essentially oscillating between 0 and that dosage concentration C0, because that's how much a single dose is affecting us. So that's the special case when Kt is really big. And remember, that means either the drug is being cleared out of the body really, really quickly, which is why you have a 0 after a certain amount of time, or I wait a really, really, really long time to take the next dose. So either way, the combination of those two things are going to lead to the amount of drug in your body going to 0 between doses. So that's one case. Let's look at the more typical case where this isn't what happens. In this case, I'm going to think about that quantity being small. So bigger than 0, positive still, but a small real number, so a lot less than 1. In that case, e to the Kt, again, if I draw e to the Kt, e to the Kt looks like that. No, it doesn't. What am I saying? The Kt axis is along here is what I'm thinking. And as I make e to the Kt, as I make Kt close to 0, then this is getting close to 1. Now, it's still positive, so I'm looking nearby, and so the y value is a bit bigger than 1. E to the Kt is about equal to 1, but it's still bigger than 1. So e to the Kt minus 1 is going to be pretty close to 0, but it's still going to be positive. And if it's pretty close to 0, but still positive, then 1 over it is going to be a really big number. So this is going to be pretty big. In other words, the residual is much bigger. In this case, this long-term residual is going to be much bigger than the starting concentration. That's what we're saying. Let's draw a graph. Okay, so not the greatest graph in the world, but you can see the idea that if K times T is small, then either the body is clearing the drug out very slowly, or the time interval is really, really quick, which means we're relatively quickly going to rise up towards this long-term behavior. The long-term behavior we saw before, where the drug is just the drug is just oscillating between the minimum dose, the long-term average for the minimum, and the long-term average plus 1 extra dose. And so if this is what was going on, the question is, how would we choose the drug schedule? In other words, how would we choose the time between doses? Now, what I know, remember from the beginning, I know the maximum safe concentration, that was our H. I know the minimum effective concentration, that was our L. They're given to us. We know K because K is how long it takes for your body to clear out the drug, and so that's a physiological thing. Drug trials are going to tell us what that is. H and L are also related to how safe the drug is, how much you can have in your body. So that's going to be a function of your body and the drug. And so we know all of those values. And the only other thing we've got to play with here is the C0. So those are essentially the quantities we want to choose. How much should each dose raise the concentration? That's our C0. Remember, all of these jumps are the same. They're all C0, even if they don't look like it on my graph. So every single one of these jumps is C0. So the question is, how much drug should I give every time I give the dose? And how often should I give that dose? Those are the two key pieces of information. We're assuming we know three other things: the rate at which your body clears it out, the highest safe concentration, and the lowest effective concentration. Let's use those pieces of information to decide what's going on here. So here's the setup we have. Eventually, we're essentially oscillating between the long-term residual and the residual plus C0. C0 is the increase in concentration from a single dose. Now, trials have told me the highest safe concentration and the lowest effective concentration. So if I'm just oscillating between those, one simple choice I could make would be to say, I'm going to set the highest safe dose at this level because I know I'm never going to get above that level. I'm never going to get above this line. This is the maximum. The maximum is R, whatever it is, plus one dose. So in reality, I might take 1.1 times that to make sure I'm above it, right? And in the same way, I can take the lowest effective dose to be this minimum, because in the long run, most of the time, there's small periods of time when we dip below it, but in the long run, we're essentially always above R. So that choice allows us to maintain the concentration in the bloodstream so that it's always, or almost always, above the lowest concentration that works, and below the maximum dose you can have for safety. So we're going to choose H to be R plus C sub 0, and we're going to choose L to be R. And wording it that way is a bit confusing because in reality, H and L are given to us. R and C0 depend on those other quantities that we know. And in particular, we know R over C0 is given by this. All right, so let's use all of this information to find the dosage schedule and the dosage value in terms of the other quantities. And the first part is actually easy, because if the top value here is H and the lower value here is K, then L, then what's the difference? Well, H minus L must be C0, right? Because this is R and this is R plus C0, so the difference between those two things is just C0. So let's go on the next page and write that down. We know immediately that C0 is the highest safe dose minus the lowest effective dose, and that's part of our prescription. So we know what C0 is in terms of these other things. Let's use what's left to find the dosage schedule, the time between doses. And it's just an algebra problem, so yay! All right, so to do that, I'm just going to substitute things in here. So I'm going to write R is equal to C0 over e to the kt minus 1. But I know what C0 is now. C0 is H minus L over e to the kt minus 1. Oh, and I know what R is. R is L. So I can just write that down. So what I've got now is L on the far left is equal to H minus L over e to the kt minus 1. And then I know everything in there except t. So just solve that algebraically. So rearranging, and so just multiplying the denominator over, expanding things out. As soon as I expand things out, I see there's a nice cancellation going on here, and I can cancel the L's on either side. And so I've got a very simple expression. We've found that L e to the kt is equal to H, and so I can solve that for t. I'm going to divide the L on the other side, so h over L. I'm going to take the opposite of an exponential, which is a natural log, and then I'm going to divide by the k. So doing that algebra gives us the dose schedule in terms of the other quantities in the problem. No, it doesn't want to make a box. Okay, so these two things tell us how to choose the amount of the dose. So remember, this is, what was it, milligrams per milliliter, and this is in time, whatever time units we're using. The time is coming from the K, they're in the same units. So someone's going to come to us and tell us, here's the maximum safe dose, here's the minimum effective dose, that's H over L. We'll take that log and multiply by 1 over K. K is how long it takes your body to clear out some of the drug. So these are experimental values that we can get, and so we can calculate then the dosing schedule and the amount of each dose. Let's have a look at a simple example of how we could use this. Right, our model is telling us that the amount of the dose is the difference between the lowest effective and the highest safe doses. And then T, the time between doses, is given by this quantity where K is the elimination constant, remember? So suppose we have these values. So suppose we have a certain drug. It has an elimination constant of 0.02 per day, which means 2% of the drug is removed every day. And the highest safe dose is 10 times larger than the lowest effective dose. How often should we take the drug? All right, so how often should we take the drug is just 1 over K times the natural log of H over L. And we know that the highest safe dose, H, is 10 times larger than the lowest effective dose. So this is telling us that H is equal to 10L. And so this is the natural log of 10. H over L is 10. And this is 1 over 0.02. And so if you calculate that, then you get these nice values. It's exactly 50 log 10, which is about 115.1. The units here is 1 over K. K is 0.02 per day. So this is in days. So we should take this every 115 days. So you might imagine this drug is something that you go to a doctor and get injected for, and you have to go see the doctor every 100 days or so to get the new injection. So if we want to maintain a safe and effective concentration of the drug in our bloodstream, then we should go and get this injection every 115 days. So there's lots of other kind of fun things we can do with this model. I'm going to give you at least some of them on the next assignment. I'll give you a problem to look at after you've watched this video as sort of an initial practice, and then some of those will, as I've said before, I think turn into our assignment problems. Okay, so I've done a lot over the last few days with this model. So have a go at some of the practice problems and then come and ask me questions. I hope to see you soon in the Zoom office hours. Ciao.